Hello everyone, in this video I'll give an introduction to our paper Lower Bounds and Improved Algorithms for Asymmetric Streaming Edit Distance and the Longest Common Subsequence. This is joint work with my advisor Xing. So first, let me give an introduction to the problem we studied, edit distance and the longest common subsequence. The edit distance problem takes two strings x and y as input, and the output is the minimum number of insertions, deletions, or substitutions that is required to transform x to y. In the example here, we can first insert a t after the first two symbols of x, and replace the g with an a, and finally delete the last symbol g in x. So the edit distance between these two strings is 3. For the longest common subsequence problem, the input is also two strings, and the output is the length of the longest common subsequence. In the example here, the longest common subsequence is marked in red. So the length of LCS of two strings x and y is 5. Both edit distance and LCS are fundamental problems in computer science. Here, we first give a brief overview of some of the previous works on these problems. For exact computation, the classical dynamic programming algorithm can solve both problems in quadratic time. If we assume that the edit distance is bounded by some number k, then the problem can be solved in big O n plus k squared time. Currently, the best algorithm in terms of time complexity is only slightly subquadratic by a factor of log n squared. And we know that all these exact algorithms is at least linear space in worst case. The recent study of fine-grained complexity has shown that any truly subquadratic time algorithm for edit distance or LCS would contradict the strong exponential time hypothesis. A recent line of research has achieved breakthrough in constructing fast approximation algorithms for edit distance. The most recent result gives an algorithm that can output a constant approximation of edit distance in big O n to 1 plus epsilon time. The key idea is to sample and compute edit distance between pairs of substrings and the use of triangle inequality. We know that all these algorithms are randomized. For the space complexity, the classical Savage theorem says that any problem that can be solved non-deterministically with space Fn can also be solved deterministically with space Fn squared. We know that both edit distance and LCS are in NL. Thus, they can be solved in log n squared bits of space in course polynomial time. For polynomial time algorithms, the best algorithm uses n times log n to 1.5 over 2 to the square root of log n bits of space. And we know that there's no truly sublinear space algorithm for exact computation. Recently, in a separate work, we have shown that for 1 plus small o1 approximation of edit distance or LCS, there exist algorithms that uses only polylog space and runs in polynomial time. Edit distance and LCS has also been studied in the streaming model. For the standard streaming model, there are strong lower bounds. For example, any randomized algorithm that can compute LCS or edit distance exactly will require at least linear space. And it is also known that even a 2 over square root n approximation of LCS in the standard streaming model would require linear space. On the upper bound side, algorithms only know when edit distance is bounded by a parameter k that is substantially smaller than n. And for such cases, there exist algorithms that can achieve k cubed times polylog n space. In this work, we study a variant of a streaming model, the symmetric streaming model. Specifically, we assume that the algorithm has streaming access to one of the input string x and random access to the other string y. For example, let's consider the following scenario. Assuming that string y is stored on a powerful server, and we want to compute the edit distance between y and many different strings. The computation is performed on less powerful computers with limited memory. The input string x is available to the computer as a data stream, and the computer can query y randomly by communicating with a powerful server. In this work, our goal is to either design algorithms with better space complexity or prove space lower bounds in this model. The symmetric streaming model can be viewed as an intermediate model between random access model and the fully streaming model. It was first studied by Sachs and Sesh in a 2013 paper. In that paper, the authors give the 1 plus epsilon approximation algorithm for n minus LCS with roughly squared n space. We know that the eddy distance can be reduced to n minus LCS. The most recent results give the 1 plus epsilon approximation algorithms for both eddy distance and LCS with roughly squared n space. And we can also give a constant approximation of eddy distance with roughly n to delta over delta space. Previously, no lower bound is known for eddy distance in this model. For longest common subsequence over large alphabet, with an omega n space lower bound, for the lower bound for streaming longest increasing subsequence, which we will discuss later. In this work, we studied both space lower bound and improved algorithms. For both eddy distance and LCS, we give lower bound for randomized algorithms when the input strings are over a large alphabet. For LCS, we can show stronger lower bound for deterministic algorithms when the input strings are over small alphabet. We also improved the lower bound for streaming LIS over small alphabet. Our paper also presented improved algorithms for both eddy distance and LCS. Now, let me give an introduction to the main results of our paper. The first result is for randomized algorithms. Assume that the input strings are of alphabet sigma and has length n. We prove that for any R-path randomized algorithms in the symmetric streaming model that decides if eddy distance is at least k with success probability 2/3. It must use a space linear to the minimum of k and the size of alphabet set, divided by R. Thus, if the alphabet set sigma has size omega n, there is an omega n space lower bound for computing eddy distance exactly. This justifies why there is no sublinear algorithm that can compute eddy distance exactly in this model. If we take k equal to 1 over epsilon, we get an omega 1 over epsilon space lower bound for any 1 plus epsilon approximation of eddy distance. A similar lower bound holds for LCS. For deterministic algorithms, we can prove stronger lower bounds for LCS. Specifically, we have shown that any constant path deterministic algorithm in a symmetric streaming model that gives a 1 minus epsilon approximation of LCS must use space linear in the size of alphabet over epsilon. Thus, for exact computation, even for binary strings, there is an omega n space lower bound for deterministic algorithms. We also proved that a similar lower bound holds for streaming longest increasing subsequence, which we will discuss later. For the improved algorithms, if eddy distance is equal to some parameter d, then for any small constant delta, we give an algorithm that can achieve 2 to 1 over delta approximation with d to delta over delta times polylog n space. This improved from previous results of O tilde to n to delta over delta space, when d is much smaller than n. We also presented a half plus epsilon approximation algorithm for LCS of a binary alphabet, with space O tilde n to delta over delta. We now give more details of the techniques we used. Let's start with the lower bound part. The proof of our lower bounds are based on communication complexity arguments. Communication complexity arguments are commonly used for proving space lower bounds for streaming algorithms. To use such arguments, we do the following. First, we assume that the local string y is fixed. The online string x is selected from some distribution. We can divide x into 2 or multiple blocks. Each party of the communication model holds one block of x, and they all have access to the local string y. Then, they communicate with each other in a certain order to compute the eddy distance or LCS. Thus, the symmetric streaming problem now becomes a two-party or multi-party communication problem. For example, consider a two-party communication scenario. We divide the online string x into two parts, x1 and x2. Alice knows x1 and y, and Bob knows x2 and the local string y. Alice and Bob wants to compute eddy distance or LCS between x and y. The communication complexity is the shortest length of messages that must be sent between Alice and Bob in any protocol, either randomized or deterministic. We can think of the information in the memory as a message Alice sent between Alice and Bob. Thus, the space needed for any streaming algorithm is at least the communication complexity divided by the number of passes of X. After transforming the streaming computation problem into a two-party or multi-party communication problem, we can obtain space lower bound by either reducing known problems with high communication complexity to edit distance or LCS, for example, the set disjointness problem, or we can construct large Pooling set. We now give more details. We first introduce our lower bound for edit distance. The proof is based on a reduction from the set disjointness problem. In this problem, Alice and Bob each holds a 0-1 string with length n. Say Alice holds alpha and Bob holds beta. If there are some I such that both alpha I and beta I are 1, then alpha and beta are not disjoint. The set disjointness problem will output 0. Otherwise, the set disjointness problem with input alpha and beta will output 1. It is known that any randomized protocol that outputs disjointness with probability 2/3 correctly needs to send at least omega n bits. Let's see how we can reduce set disjointness to asymmetric streaming edit distance. For our reduction, we assume the alphabet is integers from 1 to 6n, together with a special symbol a. We fix y to be the concatenation of 1 through 6n. Then, Alice and Bob each knows y and a 0-1 string alpha and beta. Then, Alice will build a string x1 based on alpha, and Bob will build a string x2 based on beta. We want to guarantee that if Alice and Bob can compute edit distance between y and the concatenation of x1 and x2, then they will be able to determine the set disjointness of alpha and beta. To do so, Alice first built a string alpha prime with length 2n, such that for any I, alpha prime 2i minus 1 equal to alpha I, and alpha prime 2i equals 1 minus alpha I. The string x1 is initially the concatenation of 3j minus 2 and 3j minus 1 for j from 1 to 2n. Then, for all j, if alpha prime j equals 0, we replace 3j minus 1 with a special symbol a. Bob built a string beta prime with length 2n such that for any I, beta prime 2i minus 1 equal to 1 minus beta I, and beta prime 2i equals to beta I. The string x2 is initially a concatenation of 3j minus 1 and 3j for j from 1 to 2n. Then, for all j, if beta prime j equal to 0, we replace 3j minus 1 with a special symbol a. Let's see an example. Let alpha be 110 and beta be 001. In this case, alpha and beta are disjoint. We can build x1 and x2 like this. It is easy to verify that the edit distance between the concatenation of x1, x2, and y is 19, and the corresponding best alignment between x and y is marked in this slide. The best alignment is not unique. Let's see another example. If alpha equal to 110 and beta equal to 100, then alpha and beta are not disjoint. Again, we can build x1 and x2 by our construction. In this case, due to the fact that the first symbol of both alpha and beta are 1, we can add an additional matching between x and the first 6 symbols of y. Thus, the edit distance is smaller than the previous example. Here, the edit distance is actually 18, which is 7n minus 3. By careful analysis, we can show that if alpha and beta are not disjoint, then on our construction, the edit distance between y and the concatenation of x1 and x2 is the most 7n minus 3. Otherwise, the edit distance is at least 7n minus 2. The lemma directly gives the omega of minimum of k and the size of alphabet over R lower bound for any R-pass randomized algorithm that decides if edit distance is at least k with success probability 2/3. That is for randomized lower bound of edit distance. For LCS, if we assume sigma is integers from 1 to n and fix y to be the concatenation of 1 through n, then the longest common subsequence of x and y is equal to the longest increasing subsequence of x. We know that there is a omega n lower bound for streaming LIs, even for randomized algorithms. This directly gives the same lower bound for symmetric streaming LCS. In our work, we prove a slightly stronger result. That is, the lower bound also holds when the online string x is a permutation of y. So how about the small alphabet case? Our work proved that even for binary strings, there's an omega n lower bound for deterministically computing asymmetric streaming LCS. Let's now see how it works. The proof is based on building a large Fulling set S. Again, we fix a local string y that is known to both Alice and Bob. Now, assume Alice holds some string x1 and Bob holds x2, both from some set S. We say this set S is a Fulling set if there is a function f such that the following two conditions hold. First, for any string x in S, the LCS between y and the concatenation of x and fx is equal to some integer n. Second, for any two distinct strings x1 and x2 from S, either the LCS between y and the concatenation of x1 and fx2 is not equal to n, or the LCS between y and the concatenation of x2 and fx1 is not equal to n. By a standard Fulling set argument in communication complexity, we have that the computing LCS deterministically has communication complexity at least log of the size of S. To see how the construction works, we assume the alphabet consists of two elements A and B. The local string y is simply divided into three even blocks, such that the first and the last blocks are all A's, and the middle block are all B's. The set S consists of all strings, that is, blocks of A's separated by blocks of B's with length 10. Each block of A's has length at most 9. We require that there are n over 30 minus 1 blocks of A, and the sum of lengths of A blocks is n over 6 plus 5. It can be easily shown that the size of such set S is 2 to the omega of n. We also define the function f to simply delete the first 10 bits of x. Let's see an example. Let n equal to 120 and consider any x in S. The LCS between y and the concatenation of x and fx is represented by the alignment in this slide. It has length 65, which is n over 2 plus 5. If x1 and x2 are not equal, say in x1, the three blocks of A has length 9, 9, and 7, and in x2, the three blocks of A has length 7, 9, 9. Then, due to the fact that the first block of A is longer in x1 than in x2, we can find an LCS longer than n over 2 plus 5. In this example, the LCS between y and the concatenation of x1 and fx2 has length 67. Following that idea, we can show that for all x in S, the LCS between y and the concatenation of x and fx is always n over 2 plus 5. And for two distinct strings x1 and x2 from S, one of LCS is strictly larger than n over 2 plus 5. Thus, S is a Fulling set. Since S has size 2 to the omega of n, we conclude that any deterministic asymmetric streaming algorithm for LCS is at least omega n space, even for binary strings. We can extend our construction to get strong lower bound for approximation version of LCS. The idea is to combine our construction with ideas from our previous work of Ergen and Jory. Instead of the two-party setting, we need to consider R-party communication model. We first divide X into R blocks. The ith party holds the ith block of X and has access to Y. In this model, each party speaks in turn. The ith party can send a message to the I+1's party. We introduce some high-level ideas. For this proof, we consider alphabet of size 2R with elements A1 to AR and B1 to BR. The set Si is a Fulling set we constructed earlier, but over alphabet AI and BI. And the string in Si has length roughly 1 over epsilon. We consider a matrix of this form, where each element Xij is a string from set Si. That is, each row of this matrix has a different alphabet. We consider a 2R party communication setting, where each player holds one column of the matrix. In the LCS problem, the online string X is simply the concatenation of columns of the matrix. The goal of the 2R parties is to decide between two cases. The first case is that for any I and j, xi2j minus 1 is equal to xi2j. The second case is that there exists some I in R, such that for at least R over 3 j's, xi2j minus 1 is not equal to xi2j. We can show such a decision problem has communication complexity omega r. Also, we can reduce this decision problem to approximating LCS between X and the local string Y. Our construction can be used to prove the following lower bound. For any epsilon larger than 0, if the square of the size of alphabet of epsilon is at most n, then any constant path deterministic asymmetric streaming algorithm that outputs a 1 minus epsilon approximation of LCS needs at least omega of the size of alphabet of epsilon space. Similar analysis can be used to achieve better lower bound for streaming LIs. In our paper, we also consider the variant of LIs, the longest non-decreasing subsequence with threshold. We call it LNST. For any number t, the LNST is the longest non-decreasing subsequence, where each symbol appears at most t times. LNST can be viewed as a natural generalization of longest increasing subsequence and longest non-decreasing subsequence. When t equal to 1, LNST is the same as longest increasing subsequence. And when t equal to n, LNST is the same as longest non-decreasing subsequence. We obtain the following lower bounds for approximating LNST. We want to mention that our lower bound for LNST implies a minimum of square root n and the alphabet size lower bound for streaming LIs. Previously, only square root n lower bound is known when alphabet size is omega n for approximating LIs. Finally, we'll give a brief introduction to our improved algorithms. Previously, we can output a big O of 2 to the 1 over delta approximation of added distance with roughly n to delta of delta space. The idea is to divide X evenly into n to delta blocks, and for each block, we recursively find the approximate closest substring in Y. Then, we combine these results using triangle inequality. In our work, we improve the space complexity to roughly d to delta over delta, where added distance is equal to d. The main idea is that instead of divide X evenly, we divide X into d to delta blocks according to the position of added operations. For longest common subsequence, for any positive epsilon and delta, our work gives a half plus epsilon approximation of LCS for binary strings, with space roughly n to delta over delta. The algorithm is based on a slight modification of the algorithm presented by Rubinstein and Zheng, whose key idea is to reduce approximate LCS to approximation of added distance. Okay, that's all. Thank you for watching. Bye-bye.